So what we want to do in hypothesis testing is find ways to look at sample data. Again, you can't prove things absolutely with sample data because you're getting a partial picture of a population. But somebody's making some statement about a population, and we want to be able to use sample data just to see if the data are in support of that statement or if they are not in support of the statement. And so basically, this is not an infallible process, but it's using evidence with probability to see if what people are saying is likely to be true or not. Okay, and these start pretty simple. We're going to begin with population, with proportions from entire populations. And so in section 8.2, it's a pretty simple hypothesis test. What we want to do is just remind ourselves of the basic facts about proportions. So I'm going to pop back into 7.2. I think my screen may be frozen. So let me try and get that going. Okay, so going back to 7.2, see if I can find it real quick. Here we go. And there was a thing in there called central limit theorem. And it talks about sample proportions. Remember, we use a sample proportion to prove we'll be using it to try to prove something about a population proportion. So the population proportion is always denoted as a P, okay, where a sample proportion is going to be P hat. So maybe I'll denote that here. P hat is a sample proportion. But we use it to try and determine the nature of the population proportion. Okay, and one of the things we've learned, of course, we're going to use probability in this. So one of the things we've learned is that sample proportions are approximately normal in their distribution. And that's what allows us to determine likely values and unlikely values for sample proportions. But there were conditions that n times p and n times p have to be at least 10. And what those were, you may remember, n times p is the mean number of successes in a binomial experiment, and n p is the mean number of failures. And those have to be at least 10. So those numbers are actually the lengths of the left tail and the right tail of a binomial distribution. And that looks like a bell curve as long as the tails are long enough. So that's what those criteria do. Okay, also, so we know that sample proportions are normal in distribution with certain conditions here. But also, so that's the shape, but don't forget there's also center. The mean of sample proportions is the population proportion, and spread, which is the standard deviation or standard error. So this is the standard error of sample proportions. We're going to need all of these to do probabilities for sample proportions to determine when we have strong evidence for some claim about the population proportion. All right, so that's how this is going to work. We can go ahead and just jump into this. It says, in this lesson, we begin the study of hypothesis tests. In this lesson, we test claims about a population proportion, and here's an example. Okay, here we go. It says, in a random sample of 1,100 voters, 516 say they will vote for the Democratic candidate for president. Test the claim that a minority plan to vote for her using a 5% level of significance. Okay, so we have to gather sample data, and we also have to check for normality. So let's add this. Oh, actually, you can't do that in this step because you need a value for p. I'm going to pass on that statement. Okay, so sample data. Well, you know that you'll need a sample proportion, so p hat is the sample proportion, and the formula was always the number of successes over the number of trials. And you can see up above, there were 516 successes divided by 1,100 trials. And with anything related to proportions, we like 3 significant figures. Okay, so it looks like 0.469. Which is a minority. Remember, the claim is that a minority plan to vote for the Democrat. So this almost 47%, it is a minority, but I don't know if it's within the margin of error or not. So if it's within the margin of error of 50%, then we may not be able to say this is a minority because you know, things aren't as clear when there's a margin of error. Okay, so we do need a level. I'll go ahead and denote the sample size. Of course, n is 1,100. Those are the sample data values that we needed. Level of significance is alpha. Okay? And this is just going to be a rule, and I'll go ahead and write this down. The level of significance is 5%. It says 0.25 is the level of significance. Okay. And this is just a rule for how improbable an event should be to be statistically significant. So a rule for, let's just say how probable. An event should be to be considered statistically significant. And just keep in mind, you know, significant events shouldn't happen every day. They shouldn't be happening all the time. That's not significant. That's just typical. It's normal. Stuff that is significant is stuff that's sort of surprising and rare. So, you know, normally we do 0.01 or 0.05 as just a level of significance. That just means, hey, anything less than a 1% chance. When that happens, that's kind of a surprise. And so that's statistically significant. But it's very common to go with 5% as well. So that would be 5 times out of 100 or 1 in 20, which to me is just almost not as significant anymore. So normally we don't go much larger than 0.05, but it's up to the researcher. And there are reasons for picking larger values for this Greek letter alpha, the level of significance, which we'll talk about. Okay, so step 2, it says identify the null hypothesis and the alternative hypothesis. These are claims about the population proportion. We assume the null hypothesis is true, but we try to prove the alternative. Also, we have to check the conditions for approximate normality. Okay, so let's just say in general, I think I'll block this off here and do this in 2 sides. So H0 is the null hypothesis. And it always says population proportion is equal to some number. Okay, some proportion, you know, between 0 and 1. Okay. And you know, again, you're testing a claim, and so people can claim anything. They don't usually claim the null hypothesis, so that's the tricky part. What people usually claim is the alternative. So you'll see me doing the alternative first, typically. Okay, so you have to pick one of the following statements for the alternative hypothesis. It can be that the population proportion is less than the value above. I'll say the same number. Okay. Or you could say the proportion is greater than that same number, as in the null hypothesis. You can also do not equal. So these are inequalities. You're saying what the proportion isn't when you do the alternative hypothesis. But there's three ways to say what it isn't: less than, greater than, and not equal. Okay. Any questions here? You need to see an example, so let me back up and just see what they're claiming. See, here, it's a simple statement. It says, test the claim that a minority plan to vote for the Democratic candidate. So what proportion is a minority? Anybody? So less than what percentage? Wake up, wake up. Are you awake? So what makes a minority? Less than what? Thank you, Susan. So less than 50%. So you should say that P is less than 0.50. That's their claim. Okay, basically they're saying the candidate's got a minority, the candidate's going to lose. Okay. And the null hypothesis, what you have to do is the same number. You have to say, well, we're going to assume it's equal to 50% because we'll be comparing to 50%. When we look at the sample data, it should, we notice we did in the sample, we got 46.9%, so that's less than 50. So that seems to support what the alternative hypothesis is saying, that it's less than 50. Let's make a note here. Less than 50% is a minority. Okay. But they can say it's a majority too. I mean, it's up to them. The sample data, again, 46.9% seems to support this, but remember there's a margin for error in that statistic. And so mostly this process is making sure we're not fooled by that error that comes about when you sample. Okay, any questions? Next, it says compute the test statistic. This gives the number of standard errors that the sample proportion lies from the population proportion that we're assuming in the null hypothesis. We're going to see how many standard errors our p-hat value is below the mean. So the test statistic is just a z-score. Okay, and we abbreviate it TS a lot, so I want to make sure you see that. So it's z equals, so we're going to take the p-hat value and subtract the mean of p-hat values and divide by the standard deviation of p-hat values. That's how you take a z-score. Okay. Oh, and I skipped something, so I'll go back to that in a sec. Okay, so our p-hat value was 0.469 up above. But let's go back and remind ourselves what the mean of p-hat values is real quick. So I have to go back to what we were looking at in 7.2. This was again the central limit theorem. The mean of p-hat values is the population proportion. So that is to say the mean of sample proportions is the population proportion. And the standard deviation or the standard error of sample proportions is this thing. So maybe I'll just copy that and paste it into the lesson that we're working on now. Okay, so in general, when you do your test statistic, you're taking the sample proportion, subtracting the mean of sample proportions, which is the population proportion, and dividing by the standard error, which is the square root of PQ over N. Okay, that's great. And so again, let's pound this out. A little note maybe is that you get P from H0, the null hypothesis. Okay, and then don't forget there's a Q down there. Q is 1 minus P, as you know. Okay, so P hat, again, 0.469 up above. Minus P, from the null hypothesis, we're assuming here that the population proportion is 50%. Okay, so we'll put in 50% here. And then down below, again, this is not P hat, so be careful. That's P. And again, P is 50%. Okay. Q would be 1 minus 50%, and of course, that's also 50%. So 0.50 times 0.50 for P and Q, and then over N, which I think was 1100, back up. Yeah, you see it's 1100 up there. Okay. So, and again, I think it's best if you try to do this in one shot on your calculator to eliminate the rounding errors. So let me show you real quick here on my calculator. Okay, so just start with a fraction. And remember, P hat was 0.469, so 0.469 minus P, which is 0.50, or just 0.5 if you like. And in the denominator, square root for the standard error. Okay, and a fraction inside that. And it's 50% times 50%, so 0.50 times 0.50. And then the sample size goes down here, and that was 1100. So we're just sort of building the standard error in. It's just a normal z-score. And hit enter, and it's negative 1.96, I guess we'll say. You can say negative 1.961 if you like. Okay, any questions about that? Okay, and you know, the precision is, I'd say at least keep a couple places after the decimal on this, so don't round these too much. Because your next step is going to be to determine how probable this is. You know, how likely is it to get something this low if the null hypothesis is true? That's kind of the idea. How we're going to see how probable this value is. And you can see on the next page, we're going to use the normal distribution for that. That is assuming that the sample proportions are normal. Now, one of the things I skipped is this version of determining normality for sample proportions. So I'm going to have to go back here and make sure we do the conditions for approximate normality in step 2. So let's make a little space. I'm just going to kind of squeeze that in here. And again, this is about checking that the left tail and the right tail of the distribution, the binomial distribution, that those are long enough. So you have to check that NP, which is the length of the left tail, is at least 10, and NQ, the length of the right tail, is at least 10 as well. Okay. And again, I would say you'll have to get P from the null hypothesis, and this thing does ask you to use P here. So let's make this note apply to that as well. Okay, so again, the reason why we have a null hypothesis is so that we'll have a number to use for P. And we're trying to disprove the null hypothesis, but until we do, we'll assume that P is 50%. Okay? So here comes the check. NP is 1100 times 0.50, which would be 550. So that's really long. That's definitely at least 10. And then NQ, same thing. So you can see the tails have exactly the same length. So this is actually a really symmetric distribution, and it's going to be very much a bell-shaped curve. And their tails are the same length. And looks real nice. They always come out symmetric when P is 0.5, which is that 50-50 mark. Okay, so we got the normality. Got it covered, and I guess I should say approximate normality. Nothing's perfectly normal. And so now we can use the normal curve, and the goal now is to see how probable it is to get this sample proportion. Remember, the sample proportion is 0.469. How probable is it to get something that low if the population proportion is 50%, like we're assuming? Okay. So that's, again, going to use the normal distribution. We've just determined the distribution of sample proportions is normal. So we're going to go and do some work with the normal distribution right now. Okay, so the first thing is we're going to do a thing called a critical value on the normal distribution. The critical value this is basically a rule for the number of errors that we'll consider statistically significant. We've always said 2 standard errors is significant or unusual, but this one gets a little more precise. But it's basically taking that 2 standard error rule and refining it, okay? So this is a rule for the number of standard errors required for statistical significance. And if you think about it, I'm going to go back up and remind you of the alternative hypothesis, which is what we're trying to prove right now. You're either trying to prove that P is less than some number like 50%, greater than a number, or not equal to a number like 50%. So if you're trying to prove that the sample proportion or the population proportion is less than 50%, you're going to need a sample proportion that's less than 50%. And being on the left of 50%, that would mean you're trying to find the probability of getting something that far to the left. And so we have 3 types of tests. We have these less than tests, greater than tests, and not equal tests. And if you look, I've got basically the 3 types of tests denoted here. The greater than test is called a right-tailed test here. Okay, and you're trying to just prove that you can, that your test statistic is a certain number of standard errors out here. If you're trying to prove that the proportion is less than some value, then your test statistic may better come out on the left as a distribution. Okay? And when you say that the proportion is not equal to some value, That can go in either direction, either less than or greater than. So those are called two-tailed tests. Now, if I remind you on this one, our alternative hypothesis said that the proportion is less than 50%, which makes this what we call a left-tail test. Okay. Now, to determine the number of standard errors required for statistical significance on a left-tail test, we draw ourselves a bell curve. Like that. This is a normal distribution of z-scores. But because it's left-tailed, I'm going to draw a tail on the left side. Remember, z-scores are centered at 0. Okay. And we're going to look up this cutoff value. Again, this is called a critical value, which we usually denote as a CV abbreviation. Okay. And the area of the tail that defines this critical value is alpha. That's what we called the level of significance before. And I think on this one, the alpha is 0.05. Let me double check. Look at the top. Alpha is 0.05 on question 1 here. So that's the area of this tail. Okay. All right, and again, so this will take us down into a 5% probability region if our test statistic goes down there, but I don't know until I know what the critical value is. Okay, now it says, if you look at the instructions here, it says we're gonna get our critical value in the bottom row of table A2. That's where a bunch of z-scores are stored. And this time it's gonna be under one-tailed tests. Whenever you guys used this in chapter 7, you were looking this up under two-tailed tests. So just real quickly, let's pop up to table A2. And I'm gonna have to dig for it. There we go. And it says it's in the bottom row of the table. So you have to, what you want to do is under a one-tailed test this time, we want to find our alpha. Here it is, I've just highlighted it as 0.05. So that's the area of the tail here. And then you have to go all the way to the bottom row of the table to find how many standard errors that is. And then highlighting it here, and I'll zoom in just a sec. So that's what you should see. 1.645 standard errors is statistically significant when you have a 5% level of significance. Okay, which just means there's a 5% chance of this happening when you randomly gather a sample. And we said 5% was statistically significant, and that's why we call it a level of significance. But that means 1.645 standard errors from the mean. Now, you got to be a little careful with this because we're saying 1.645 standard errors below the mean. So you're going to have to make this critical value negative. We put in a negative 1.645 as our critical value. Okay, and this is the thing that decides whether our statistic is statistically significant or not. Okay, now remember, our test statistic up here was negative 1.96, okay? And so that's going to be a little deeper into the tail. I'll put a mark right here for our test statistic. That was the z-score we computed. Okay. Because it falls into this region we call critical region, or that I colored green, we'll say, okay, that statistic is statistically significant. So let's just make a rule here.
Professor?
Yeah.
I think you put wrong number in your calculator for n. You put 1,000. instead of 1100.
Really?
Yeah.
Ah, you're right. When did you notice that? Thank you.
I
So
just
the
realized that. Yeah.
okay.
Okay.
Will you so I've done it again, but what did you get for the correct value?
I got negative 2.056.
You're the best. Thank you so much for that.
Problem.
Awesome. Okay, so it is a little different. I don't think we have to change the picture down here because we didn't denote the value, but it's still down there into this green critical region. Okay, and so the rule I wanted to put down here real quickly is just that anytime the test statistic goes past the critical value into a tail, it would be considered statistically significant. So whenever the test statistic then statistically significant is what we've got. And that's kind of important. We hear that in research, people are always saying, you know, it was significant or it was not significant. Super important to understand what they mean when they say that. Okay, any questions about that interpretation? So in this case, again, our test statistic was negative 2.05-ish, I think. Yeah, 2.056. And maybe I'll just kind of denote this. I'll just squeeze in the word significant here because it is in the tail. Any questions? Okay, so sometimes, just to let you guys know, this is a step that is skippable. We're going. I want to have you go ahead and do this in the homework. Sometimes on an exam, I won't ask you to do it because it's a little redundant. The next step can tell you significance as well. So it's important you understand what a critical value is because there are cases where you're not going to be able to do uh, the next computation, which is called a p-value. So there's a little bit of redundancy in this next step. So if I ever skip a step, it would be step 4. Okay? I'm not going to say it's optional here because I want you to go ahead and do it in your homework. Any questions? Okay, let's go on down to step 5. This is actually the really important one, which is called a p-value. And it's the same kind of idea. We're using the normal distribution, so we definitely need the criteria for normality to be satisfied. P-value is the probability of getting a test statistic at least as extreme as the one we have. So if you think back, our test statistic was a negative 2.056 here. And so what's the probability of getting something that low? Okay, that's the p-value, negative 2.056. Now, it's the same issue. You've got the right tail tests, the left tail tests, and the two tail tests. And remember, this is determined by the alternative hypothesis. So if H1 has a p greater than something, that's right-tailed. H1 saying p is less than something makes it left-tailed. Or if H1 says that p is just not equal to something, that's a two-tailed test. Okay. Any questions? So we're doing a left tail test this time, so let's sketch this real quick. This is normal distribution, which is labeled Z, and 0 is in the middle. And down here on the left, we should have that negative 2.056 in there. Yeah, that's our test statistic, negative 2.056. Okay, and then we're trying to find how probable it is to get a value that low, and that's called a p-value. P for probability. Okay, now normal probabilities, it says, come from table A1. With your calculator, if you bought the TI-36 that I was recommending, the TI-36 also does this, so I'll show both of those. Okay, any questions, anybody? Okay, so let's go to table A1. This gives areas to the left of Z, so which is what I want because we're doing a left tail test right now. Okay, so let's take a quick look at this guy. So maybe you remember how this table works. You go out negative 2.0, and then you're going to have to go out to 0.06. This 2.056 is a little too precise. We'll just do negative 2.06. That's all the table allows. Okay, and let me pop over to table A1 real quick. Remember how to do it. Okay. Okay, so hopefully you're seeing what I see here. So we're saying this is almost a 2% chance, 0.0197. Again, we're assuming the null hypothesis is true when we do this. We use population proportion of 50% when we computed the z-score. And if that's not true, then all bets are off. But what we're saying is what we've seen here has less than a 2% chance of happening. That's pretty unlikely under the assumption that the null hypothesis is true. So maybe we should not believe that assumption anymore. We've already decided what we saw was significantly different from 50%. Okay, so 0.0197, go back. Any questions about this step? So again, I said this was a little redundant because this is also telling us that what we observed is statistically significant. We remember the level of significance is 5%. So technically, anything less than 5% would be considered significant here. I think I want to squeeze in a little statement of statistical significance and p-values in general. So just real quickly, the p-values are almost better than critical values because they're sort of a sliding scale of significance. So let's do it this way. I'm going to just have a statement that says p-value range, okay, and then how significant. Okay, so if the p-value, let's say, is less than 1%, so p-val less than 0.01, you get it? This would be considered highly significant. Okay. Let's go with a 0.01 to 0.05. Maybe we just call that significant. It's not highly anymore, but it's still significant. All right. And then if we go from a 0.05 to 0.10, maybe 5% to 10%. This is just sort of moderately significant, marginally maybe moderately significant. And then if the p-value comes out bigger than 10%, and let's just say this is not significant. So p-values are kind of cool. They give you sort of a sliding scale, as I say, of significance. So you don't have to just say yes or no. You can say, oh, it's highly significant. Okay, so just a little tip on p-values there. Are there any questions? Okay, then let's just keep going. So once you have a p-value, we're able to say, okay, this is this significant. Remember, we were claiming that anything, if you go back to the very beginning, the alpha value here is our rule for how probable an event should be to be considered statistically significant. And so our rule right now is 5%. So any event with less than a 5% chance should be considered significant. Okay, so if we go down here, our p-value was, what was it? Where'd it go? 0.0197. Okay, which is less than the level of significance, which is 0.05, and that's alpha. Okay. That means it's significant. Well, how significant? Well, we're just calling it significant. This one here in the middle. Okay. But it says make a conclusion. If the p-value is less than the level of significance, we reject the null hypothesis in favor of the alternative if it's less. Otherwise, we fail to reject the null hypothesis, but we never support the null hypothesis. I'll talk about that in a second. And you make a conclusion in plain language. But basically, it's best to kind of focus on the alternative hypothesis. So maybe I'll just do it this way. Eval less than alpha. You can say less than or equal if you like. That means you're going to reject the null hypothesis and support the alternative, which is really what you're trying to do with this test. Okay. That's all you really need to know. The opposite is true when p-value is greater than alpha. So you don't really need to remember this next part because it's implied. But the trick is we don't support the null hypothesis ever. So you have to say, don't reject H0, which is different from supporting it. You're just not rejecting it. So if you don't reject the null hypothesis, then you don't support the alternative. Okay, so that's basically how you're concluding on these. Okay, so this one, we've got a less than. And less than means that you reject the null hypothesis, which had said that the proportion is 50%. And we're supporting the alternative. Which says that the proportion is less than 50%. Okay. All right, and so we have to write this last phrase here where it says support H1. You have to put that into context and don't use any weird symbols for this. So you want to say something like, and I always blame this on the data. So we say the data. This is not your opinion, right? So the data support the claim. I think it was that the Democrat has a minority of the vote. Now, let me just read that again. Democrat has a minority who will vote for her. Okay. These are all basically the same problem. We're about to do another one, but you'll see how similar they are. And then we'll move into means. This is proportions now. We'll do means next. And once again, you'll see how similar they are. Okay, does anybody have any questions? I think I would just add to the comments over on the right a little, maybe. If you remember the null hypothesis, it says the population proportion is 50%. This is unprovable unless you survey the whole population. If you're going to say what a population proportion is, and without any margin for error, the only way to prove that is to survey the whole population to see if it's true. Okay? So they're saying it's 50%. You can't prove that unless we survey the entire population. Okay, and if you're not going to survey the whole population, you better not act like you know that the null hypothesis is true. You cannot prove it. Okay, so because you can't prove the null hypothesis, I would add that we never support the null hypothesis. Okay, and that's really difficult. The best we can ever say is that we'll fail to reject it or we can't disprove it. And people don't like statisticians for that reason. They don't like the way statisticians talk. They're very careful. It's sort of like doctors as well. You're in science, you're trained, hopefully, to be very clear about your uncertainty. And the fundamental issue of statistics is that you're working from samples. And if you're working from samples, then there must be uncertainty. And you should not act like there isn't. So we always speak with sort of double negatives, where somebody says, is this true? And we would say, I can't disprove it. It's not true, you know. I can't disprove it. So we'll say we fail to reject it, or I can't disprove it, one of the two. But that doesn't make it true. It's just like in a jury trial. You assume a person's innocent, but it's really hard to prove innocence. You should be able to prove guilt, because that's to demonstrate that somebody did something. It's really hard to prove that somebody didn't do something. So in a jury trial, in the end, we assume innocence, but you don't ever say innocence. You just say not guilty, which is to say guilt was not proven, but that doesn't make the person innocent. Okay, it's just the same thing here. Okay? You're using evidence, but not proof. Okay, going on. Any questions? I think my Zoom has frozen, so let's see if we can unlock it. Okay, here we go. It says an article claims that 20% of college students believe aliens have visited the Earth. Awesome. You don't believe this, and to disprove it, you randomly gather 850 college students and find that 190 believe in aliens, or at least they say they do. Test your belief at the 1% level of significance. Okay, so let's go to the data gathering. Remember, there's a p-hat that you need, which is x over n. X is the number of successes. These are binomial experiments. We had 190 successes out of 850. Okay. And that's with 3 places. This is called 0.224. All right, so you need that, and of course the n is 850, easy. The level of significance is a 1% this time, so that's a 0.01. Don't think there's anything else we need to worry about there. You do need to do a null hypothesis again and an alternative. So, oops. It's easier to do the alternative hypothesis. It says you don't believe what? 20% of college students believe aliens have visited the Earth. You don't believe it. Now, what I don't know is what you do think. You might think it's less than or greater, but I don't know that right now. All I know is you disbelieve it. And so to not believe 20% is to believe it's different, or to believe it's not equal to 20%. So what we're trying to determine here is if the proportion is not 20%. So remember, you can do less than, greater than, or not equal on these. Okay. But the article claims 20%, so that's your null hypothesis, and you just don't believe it. So you're going to try and prove otherwise. Less than or greater. Okay. Any questions about that? Don't forget, there's a check here because we're going to use the normal distribution in a minute. So the check, again, has to be NP greater than or equal to 10 and NQ greater than or equal to 10. So we used 20% for P this time. So NP, remember N was the 850 and P was 0.20. At least we're assuming it is. So it's 170. That's the length of the left tail on the binomial distribution. Plenty long, it needs to be at least 10, so we're good. And then N times Q, let's go ahead and do Q here. Somewhere Q is 1 minus P. So 1 minus 20% is 80%. Okay. Maybe get that? Right, okay, 680, thank you. That's the length of the right tail. So this is not a symmetric distribution, but the tails are long. They will vanish nicely on both sides. And as long as these are both bigger than or equal to 10, this will be sufficiently symmetric to say it's approximately normal. Okay, so we can do sort of a big yes to approximately normal. Any questions about that step? So with the approximate normality, we're sort of like, okay, let's go ahead and do our z-score, and we'll use a normal distribution on this. So the z-score from before, remember you're taking the z-score of the sample proportion. The mean of sample proportions is the population proportion, and the standard error is the square root of PQ over N. So the p hat that we had was 0.224. P, we're assuming is 20% in the null hypothesis. And over the square root of PQ, that's 0.20 times 0.80 over N, which I think is 850. Let's all try that out. I'll try not to put the wrong denominator in and see if you guys can get the same answer as me. So I got one here. Yeah, 1.75 is good. Thanks, Benching. 1.75. Now, is that statistically significant? Well, it's not two standard errors above 20%. We got that 22.4%. Not quite two standard errors above 20%. So I don't know. It doesn't look significant, but then we have to be a little more careful and look at this thing called a critical value. Any questions here? Okay. So we've got this 1.75 test statistic. There's a thing called critical value on the bottom row of table A2, gives the number of standard errors for statistical significance. Now, just want to remind you what kind of test we're doing. The test is determined by the alternative hypothesis. So H1 said that the proportion of people that believe in aliens is not 20%. Not equal means less than or greater than. Either one of those. So we don't care what side the statistic falls on. It could be the right or the left. Okay. And if you go back to the diagram here for critical values, whenever if the alternative hypothesis says that p is not equal to some value, those are called two-tailed tests. Okay, so we're going to do a positive and a negative critical value. And notice the tails get divided, and the area gets divided by 2. So it's not alpha anymore, it's alpha over 2, just like in a confidence interval. And we want the probability of falling into a tail to be alpha, but there's 2 tails. So you have to divide the alpha up amongst the 2 tails. Okay, so, and I don't really care what alpha over 2 is. The table takes care of this. Okay, but let's look this up real quick. So this is table A2. They say bottom row where all the z-scores are. So remember there's a degree of freedom column. Just ignore degrees of freedom. Go to the bottom row where it says large z-score. Okay, and this tells how many standard errors. Our alpha this time, I think, was it 0.01? I don't know. Yeah, 0.01. And it's two-tailed, so this is going to be pretty large z-score compared to our test statistic. Okay, so let me pop over to that real quick. Bottom row, so let me get that real quick. So let me zoom out. 0.01 two-tail is the first column. So all the way down the bottom. I think it says 2.576. So that's how many standard errors is statistically significant this time. That's a lot. And we didn't get anything close to that. Okay, any questions about this? Remember, it's two-tailed on this one, so make sure you're looking under two tails. That's the tricky part. Two-tail test, you have to do two tails. Okay. 2.576. Let's put this, let's copy this over. Okay, now it's two-tailed, so you got to do plus or minus. We're saying different in either direction here. So do plus or minus on your z-score here. 2.576. These are called critical values. Just abbreviating that with CV for critical value. All right, so that's the definition of statistical significance. We did not get anything close to that, so let's make sure we see our test statistic on here. Test statistic going back was 1.75, so 1.75 is going to be down here maybe. And that's not significant because it's not the number of z-scores required by a critical value. Okay, any questions? Okay. So now is this thing called a p-value. This is a probability of getting a statistic at least as extreme as the one we have. Okay, so and this probability should be less than 5%. So let's go on to this step. Okay, so we'll put in our 1.75 here. That's the test statistic. Okay, but we're trying to find, remember the p-value is the probability of getting a test statistic at least as extreme as the one we have. Now the tricky part here is to be at least as extreme as 1.75 standard errors from the mean. On a two-tailed test, that could go in either direction. So we're saying 1.5 standard errors. But we're saying the alternative hypothesis says it's just different. Okay, so not equal means less than or greater. So we're allowing either direction on this. So over here, I'm thinking about negative 1.75 standard errors as well. So this is the negative of the test statistic. And I'm really going to count both of these tails for the p-value. Effectively, that means we're just going to look up the area and double it. Okay. So you can look up the positive 1.75 or the negative, but make sure you're getting the area to the left. So if you go to table A, if you go to table A1, and for your z-score, you look up what we actually got, which was negative 1.7, sorry, positive 1.75. If I can't seem to do it, here we go. 1.7 plus 0.05, like that. Let me pop over and see what that looks like. Now I think you're seeing a 0.9599 here. And remember, this is the area to the left of your test statistic. And we actually are wanting the area to the right. Okay, because we're doing the right tail right now. 0.9599. So that's the area to the left. This tail is going to be 1 minus 0.9599 because you want the area to the right. Okay. This would actually be easier if you just look up the negative 1.75 because it'll directly give you the area to the left. This table only gives areas to the left. Anybody get that? Anybody? Fine, it's 0.0401. But you have to remember, we're counting both tails, so the other tail is 0.0401 as well, because we're trying to say what's the probability of this in either direction. So you really do need to double this. So you'll see on these two-tail tests, the p-value, you have to multiply the area by 2. So you're going to do 2 times 0.0401. Just got to double that. And so that's going to be 0.0802. And that's a big p-value. Remember, anything, yeah. Thanks, Andrea. Thank you, everybody. Remember the p-value, we said if the p-value is between 5% and 10%, that we were calling that moderately significant. So it's not really going to be living up to the 1% rule that we made for this problem. It's just not, we're not going to agree on this one for significance. So coming back down here, the p-value is 0.0802, which turns out to be bigger than the 0.01, which is our alpha value. Okay. And just as a reminder, I'll put it over here. P-val less than alpha, less than or equal maybe to alpha, means you reject the null hypothesis and support the alternative. Okay. Otherwise, you do the opposite. So p-val greater than or equal to alpha means that you don't reject the null hypothesis. And you don't support each one. You'll need to remember this. It's always the same, so we're going to do hypothesis testing for the rest of the semester. Yay! And this rule that I just put up is just universal. So this one's greater. Oh, I say greater than or equal, you guys. That's a mistake. This should just say greater here. On the second rule there, p-value greater, not greater than or equal. Okay, so in this one, our p-value was greater than alpha. So this one's a rejection, sorry, failed to reject. On the null hypothesis, which means we don't support the alternative. And remember, we're trying to prove the alternative. So we don't support H1 that says that the proportion is not 20%. So the null hypothesis said the proportion is 20%. So, and then you just need to put that into some plain language. Again, it's probably best if you talk about the alternative hypothesis. It's really easy in a jury trial to say guilty, but it's trickier to say when that's not true. You can't say innocent, you have to say not guilty. But no, it's just complicated with the null hypothesis. So focus on the alternative. Either you're supporting this or you're not. And we always blame this on the data. So the data, this time, do not support. Remember, they do not support because data is plural. So the data do not support the claim that the proportion, I think it's US college students, so proportion of US college students who believe in UFOs, I think is what it said. I'm gonna check. Don't believe aliens have visited the Earth. Awesome. Who believe aliens have visited Earth. Is not 20%. So you're wrong. You're saying it's not 20%. And we're saying the data do not support you. Okay, again, I'm wrong. It doesn't mean you're wrong. It just means the data do not support you. But you don't have evidence for your belief. Okay. Data. Any questions?